Good afternoon, everyone. I know that it's a very long day and you seem to be very tired, but this is a research, so we have to be patient. My name is Mohamed Elamin. I'm from Sudan, University of Science and Technology. I'm doing my research in survival analysis field. I conduct this research with the group of professionals in the University of Malaysia. So I'm doing the research there. So I'm very happy to share with you my experience in this field. So we go through the introduction and it's about its review and material and method and result and discussion, conclusion and references. By the way, I'm talking about the utilization of XRQ model based on the generalized modified value distribution for the analysis of leukemia patients. Acute leukemia, which is known as AL, is a form of bone cancer involved with cancer located in the bone marrow, in blood, and other slides. The risk of this disease is very high in the younger than 5 years in children, and there is decreases slowly until the age of 20 and begins to rise slowly until the age of 50. Based on the American Cancer Society, the estimate of US in 2020 are about 6,660 new cases, almost 6,740 males, and the remaining in the females. About 260 deaths from the disease, 880 males and 630 in the females. The main treatment of this disease is chemotherapy, which is comprised of induction, intensification, and long-term maintenance with central CFC and CS, which we provide at different times of the therapy. What is the function or the purpose of the induction therapy? This purpose is to complete remission and restore normal levels. And we know that the complete remission is that there is no evidence of leukemia after the treatment. Following this induction treatment, patient undergoes 3 cycles of induction, consolidation, and treatment, which is associated with leukemia rescue and aspirin. Leukemia patient with a high-risk disease and multi-donor then disease or disease considered. The risk were randomly assigned to start the consolidation maintenance or what you call autoimmune system cell transplant. This is based on Weibull 2017. The model that we use here, we use a mixture model, which is the pioneer work of this model is done by Watt in 1994. In 2014, it was for survival data with the human model, Q fraction. Use that non-parametric approach to analyze the impact of one factor or one predictor that in the proportion of the Q patient. 2017 Goldman, he modeled the incidence for that is the part of the model using a logistic model, and he left the survival function of Q hospitalization is that is unjustified. In 2018, we have Amigo and he used a single model for the carbon probabilities, and he modeled the survival function of the little using cross correlation as a model. In survival analysis, it is known that the Weibull distribution is widely used in the cancer research. Why? What the idea behind that? The idea, this model has another function which is flexible, and the parameter of this model can be easily estimated. However, when we're dealing with the data in the cancer research or study, we need more advanced parametric models. Cannot be this model. So, in addition to that, there is another scenario coming in the survival analysis. Sometimes in your sample, you can find out some patients are being cured from disease. If you talk about the cancer here, they will be cured. At the end of the patient is looking from that if you follow the recurrence of the cancer, by the end of the study, we find out some patients that are still cured. So in this case, we give this subject or in this category is a cured or unsuspectable patient, which is very important. So how we know that in our sample there is a cure after the survival? Maybe as a physician you know that by having background about the patient, you know that some of them are cured after this one. But statistically we don't agree on that, so we have to run what we call Omer. And then in this figure here you can see the first one is the left. This is the tabular model, estimated based on the our study. We applied the leukemia data. We found that the graph is extremely unstable and level of around 0.3, indicating that there is a cure fraction in this sample at the end of the observation line. The panel to the right, we have two groups. We have allogeneic group and we have particular group. In both of them, there is cure path. So for the allogeneic, we have around 0.28, and for allogeneic, we have 0.3. So based on this, we can conclude that there is existent fraction in this system. Whenever we know that we have any idea before this, but I think the statistically it proves that. So in this case, the researcher usually use a pure fraction model. They never use the parametric model because in this case, the parametric model maybe overestimate the parameters. Since we know that there exists pure fraction, so we have to use a pure fraction model. So the problem is that which distribution outcome I use for the uncured subjects? Here is the challenge. So the purpose of this study is to select the best distribution for uncured patient. Uncured patient sometimes we give them the unsuspectable patient or uncured patient. So in this study, we focus on the leukemia patient data, and we use generalized modified distribution, which I made by EMW. And its particular cases. This distribution has many such cases, and then in the few slides, I will talk about this distribution a little bit. Why we use generalized modified distribution? We use this distribution because this distribution has the capacity to model monothetic and non-monothetic failure rates. This rate of thyroid hazards is very common in cancer patient data. When we take any cancer patient data, we take the graph of the risk function, we found that it is monetary or non-monetary. So our data is the leukemia data. This data consists of 91 patients, and this is the high-risk acute lymphoblastic leukemia, which is ALL. And we follow from 1982 up to 1987 for 5 years, and then we think the initial cure. This data presented by Crispy in 1987, and it's also available in MSQR RPH software. So the data consists of two groups. The first group consists of 46 patients, which is supposed to allogeneic bone marrow transplant. The second group consists of 45 patients who receive autologous bone marrow transplant. The question is, what is the event of interest? The event of interest is the time to test. So after the operation, immediately after transplant, we're following the patient until the time of test. If the test is happening, we said that it is the failure is happening. But when we analyze the data, we have around 24% they arise sensor observation. I would like to talk a little bit about arise sensor observation because this is the statistical field which is somehow it's out of the scope of this conference. But anyway, I can give brief what we mean by right sensor. But when we have an experiment and then we have starting for the experiment until the end of the experiment, for example, I'm interested in the time to test until the end of the observation period. For some subjects or for some patient, the test is not happening. So all these subjects that is after the end of the experiment that is still alive, you call them right sensors. Or in between, because sometimes the patient comes to the clinic and then for the following up. For example, in the last following up for some patients, they come in. Then after that, for the next visit, they're not coming. So what do we know about them? We know that they come in for the same, for example, same visit, but between the trial. Maybe they die, maybe they die due to another reason, not the cancer. So in this case, we have partial information about them. So also we give them right sensor. So we have in this data, we have 235 sensor, and then in general we have 28, around 28% for the patient from the organic model, and we have 20% patient from alcoholics. So here we use this indicator of the again, one for observed lifetime, which is that the event is happening, and zero for sensor lifetime, which is disappear or we have partial information. So this is a model, generalized variable distribution that we use. Equation one here is showing that there is the function. I use F star GW is that this generalized variable distribution. This is the mathematical equation. And then equation two is S star GW, which is for the variable function for this model. And use alpha and gamma and beta lambda. Alpha and lambda are scale parameter, gamma and beta are resulting shape parameter. So, as I said, the generalized variable distribution consists of many sub-distributions. These distributions are special cases. Whenever we take the lambda equals 0 big for this case, we get Weibull, and so on for different cases. You get, for example, homology distribution, which is written by E, Raleigh, extreme value, exponential, generalized value distribution, and modified value distribution. The whole of this L distribution are some of the main models in GMW. In this study, we use all these models to identify which one of them will be suitable for our leukemia data that we need to study. So we use our mixed Q model, and then here we have equation 3, which is a very important equation. To the left, we have the survival function of population. And now here we have two parts. We have rho of X, and we have this part, which is S2 and K. I will tell you this one. From the name of the model itself, mixture Q. So in the mixture Q model, the population is divided into two parts, the Q part and non-Q part. So this is the reason why it's combination. So we use maximum likelihood estimation to find the parameter of this model, and then we use the log likelihood function to use maximum likelihood estimation to get the parameter estimate, and then we use also this model to study the covariant influence in the survival function, and then we use this model for connecting the covariant with the Q fraction to see that is there any effect of any other factor that affect the ratio of the Q and the Q. So how we compare this study? We compare with them by using a kind of information criteria, AIC. Now, if the value of AIC value is small or lower value, in this case, the model that provides this value is the referable model. So this is the reason how one well built we can make the comparison. So in our results in table 1, we have the role of the value that we have here, and then as you see for generalized variable distribution, AIC is 955, and for EW it is 936. From here, we know that these two models provide the best fitting of our data that we use. So table 2, we do the same, but in this case, we remove the Q fraction, and then we find that the values of AIC becomes greater, indicating that all the models that ignore the Q fraction in the data study, they overestimating and they are not suitable for it. Now, in this figure, we fix and visualize the relation between the product limit estimate for the survival function and the anticipated values. It's very clear that generalized variable distribution and associated distribution provide best fitting of this data. The other models cannot provide it because they do not have a good relation between anticipated value and product limit estimate. Here, this is our analysis for survival function and for the other function. From here, we get that the values to the left, we have Kaplan-Meier estimate, and we have generalized variable distribution with the rest. And to the right, also we have the same We have Kaplan-Meier and we have generalized modifier. Comparing panel A with the panel B, which represents the survival function, we found that the generalized modifier distribution and subordinated distribution provide the best survival function, which is closer and closer to the Kaplan-Meier, which indicate that these are very valuable and very important. Now, if we look at the panel C and panel D, here we have the hazard function. It is the corresponding hazard for the same modified Weibull and associated Weibull. They provide best hazard we can read it and indicate that the higher is very high at the beginning and indicating that this hazard is very high after the present immediately. Here, after we know that the base model is generalized modified Weibull distribution, we focus on this model and focus on the estimate value for each one, and we have focused on the 95% interval for each parameter. If you look at the row one is the fraction of the pure patient in allogeneic, which is 0.7, and this is the 95% coverage table. Row 1 for the autologous group, which is 0.915. So if we get the ratio between the enrollment over row 1, we find it is 1.49. And this is very important values. We found that the 95% confidence interval, which is 1.18 and 1.730. This interval is not included the value 1 and it has very variable meaning. I suggest it later. Now, in this graph, we found that this is the hazard function and this is the time. For the red curve here, this is the hazard for the death when we apply the allogeneic treatment, and then with the blue one for autologous. It's clear that the hazard of death is very high after the 11 days from the main transplant for allogeneic. And around 33 days, it is the hazard for if you consider autologous. And you see here that these two curves are overlapping. This means that we cannot use the Cox model for analyzing this data. We only use the pure model. And then around 100 days after the surgery, almost the hazard will be the same and decline and decreases until the end of the observation time. So, what we conclude from here? We conclude that the ratio of row 1, which is the confidence interval is not including 1, do not contain the value of 1. What does this mean? This means that there is a proof of difference if we treat the patient using autologous or organic, and we make inference in the population. From this sample data, we can say that using this type of treatment for treating the cancer, using both of them, based on the population, there is no difference between them because there is a difference between these two groups. So you cannot treat the patient with allogeneic or regular stem population. They have different, and they have different results. The finding of the shown that, as I said, that 11 for the negative side for allogeneic, I said 12 days for autologous, and then after 40 days, the hazard of this is almost the same. So from here, we know that the mixture pure model based on general distribution is suitable for this, and the Kaplan-Meier is said that the probability of being used for allogeneic group is better than the survival of autologous. This is the sample. But as I said, compare this for the population, it's almost the same. We have to be aware of that. And this is also presented that the found mixture pyramid is based on generalized modified Weibull distribution or exponentiated Weibull. This is the better fit leukemia data. And then based on the study conducted in 2018, Kotel estimate the rate of allogeneic and autologous group and use different kinds of approach. Use the same method that you use monogenetic distribution. We found that 0.29, 0.239, and 0.24, respectively for allogeneic and autologous. 2020, Lazaro also conducted the same study, but used different approach, and he found that the value is 0.7 and 0.98. Both of these two studies are consistent with our finding, and if you compare our finding with this study. So The last thing we have to say that we have to focus on parametric models. They are specified distribution for the Weibull mice. They are appropriate instrument for analyzing the data with long-term survival. So if you make that there is long-term survival, so we have to use parametric cure model. So also, it is very important that for all the physicians working in the field of survival analysis to know how to do this analysis, because knowing the fraction of the group people that will be cured is very important. And then also their knowledge on using maximum likelihood estimation, they have to know this one. And then at the end, I said that subordination and generalized distribution are the best choices for the survival time of the key emission compared with generalized distribution and it is less. And thank you very much for your attention. I know that maybe I don't know your background in statistics, but anyway, I'd like to share this and focus on the thing that it is very beneficial for the statistician to know these things when they decide that which type of treatment they have to go with based on the statistical data. Yes, thank you very much. And